this video, we are going to cover the chemical reaction known as catalytic hydrogenation, which involves the reduction of alkenes into alkanes. In this example here, we have the reactants and the products of a catalytic hydrogenation reaction. Here we have the hydrocarbon 2-pentene reacting with the H2 molecule in the presence of the catalyst platinum to create the reduced product of pentane. Recall that the reduction of a molecule involves the addition of hydrogen. That is what you are looking at here compared to the reactant counterpart lacking 2 hydrogen atoms. Also notice the effect that this reaction has on the bonding pattern between carbons, a double bond compared to a single bond. The reaction gets its name catalytic because a precious metal such as platinum, palladium, or nickel must be used in order for it to take place. The metal catalysts do not appear in the product, but they do need to be present for the reaction to occur. So here we have just the reactants of the previous reaction to explain the process in slightly more detail. Notice we have color-coded some of the molecules and bonds to make it easier to follow along. I have also changed the platinum metal to a palladium metal to emphasize that the catalyst can be interchangeable. We can visualize the H2 in this way to make it clearer. The first step in this reaction will be to move this H2 over to where the hydrogen will be added across the carbon chain. These color-coded arrows show where these new bonds came from. The double bond was broken and reattached to one of the hydrogens, while the bond on the second hydrogen dropped down to form a bond with this carbon. We now have a successful catalytic hydrogenation reaction. Mrs. Zobel, you may pause the video and attempt this problem to check your understanding before we reveal the answer.
Just do it!
If this is the product that you have, then you have done the reaction correctly.
Wow!
Regardless, I will go over it one more time to show how this reaction takes place. Again, our first step will be to move the hydrogens over top the double bonded carbons. We will then break this bond and reattach it to one of the hydrogens. And then we will move this bond from the remaining hydrogen and attach it to the second carbon. It is also noteworthy to realize that the molecule is no longer called ethene, but now ethane, due to it now having a single bond. To depict why this reaction is applicable in everyday life, we will discuss two products, soybean oil, aka vegetable oil, and whipped cream frosting, aka partially hydrogenated soybean oil.
To better explain how this reaction is applicable in real life, we will need to briefly go over two different concepts.
The first concept we will briefly discuss is saturation. Notice that whenever we perform a hydrogenation reaction, we fill the chain with hydrogen atoms. In other words, we are saturating the molecule with hydrogen. On the other hand, before the reaction occurs, there is a lack of hydrogen, or you could say that it is unsaturated. To accurately show this concept, we would have to explain and show a triglyceride molecule. But for the purposes of this video, I will be showing slightly more simple molecules known as fatty acids that are actually components of these triglycerides present in the two food products. Here we have two saturated fatty acid molecules lined up next to each other. Notice that they seem to be packed together very closely. This is due in part to the hydrogenation of the molecule. Notice this very similar fatty acid molecule that is unsaturated and contains double bonds. These double bonds often create these kinks in the chain that make it more difficult for them to pack tightly together near other molecules. The second concept we will very briefly discuss is called London dispersion forces. All molecules have a weak attraction to one another, and the closer that they are able to be to each other, the more the attraction increases. There are more details to this concept, but that is as much as we need to know to grasp the main idea. And that is essentially the main difference between the two products here, and why the vegetable oil is liquid while the frosting is a solid at the same temperature. Simply put, there is a higher ratio of unsaturated molecules in the partially hydrogenated frosting made from soybean oil than there is in the soybean vegetable oil. Using the rules that we learned about London dispersion forces, we can deduce that the saturated molecules in the hydrogenated frosting allow for them to pack more closely together and have a stronger attraction to one another, which allow them to form solids at higher temperatures. The vegetable oil has not undergone this partial hydrogenation process and has more unsaturated molecules with double bonds, making them more spread out and less attracted to one another, which makes them liquids.